Alright, so this will be a continuation of my differential equations playlist, and today I'm going to be talking about separable differential equations and initial value problems, which are kind of two concepts, but they kind of, they're kind of introductory concepts because everything that we do from here on out is going to, initial value problems, we're going to be doing lots of those, and I figured separable differential equations are a good place to start because I think they're the easiest type of differential equation to solve, and once we do an example, you'll see what I mean. They're pretty straightforward, and they're, I think, a good differential equation, a good type of differential equation to start out with. So basically, separable differential equation is basically one that can be written in this form, where you have some function of y, ny dy equals some function of x, mx dx. And basically, if you wanted to solve this type of equation, it's pretty straightforward. All you have to do is just integrate both sides with respect to the independent variable of each function. So basically what that means is here we have a y, and here we have a dy, here we have an x, we have a dx. It doesn't really matter what we put here, as long as this differential agrees with this function right here, then we can integrate it, we can solve for some function y of x. That's a pretty straightforward thing to kind of grasp. It's really just integrate both sides, which is kind of like calculus 1 stuff. But basically, let me just go ahead and do an example. So here I have, dy over dx equals 3x squared y. And basically, so what do I do in order to solve this? Well, I can write it like this. I can simply just, this is actually a very important technique in differential equations where the differentials here, when you write a dy over dx, they can also be thought of as fractions. And that comes in handy in solving a lot of differential equations, not just separable. But here, what you can do is you can actually multiply both sides of this by dx, and so you're going to get, dy equals 3x squared y dx. And that's already, we already made some progress. So here, you can treat this like a fraction. Don't forget to treat it like a fraction. So if this was written like, I guess I'll just write it down here. If this was like, y prime equals 3x squared y, usually you can rewrite that as this, and you can see that it may be easier to solve. Some people can visualize it better that way. I like to usually write it this way when I'm solving separable differential equations, because you can just get rid of the fractions. But yeah, that's just an aside. It's not really that important. Basically, what we're doing here is we're simply just trying to separate the x's and the y's. So how is that going to do with that? We can actually now divide both sides of this equation by y, and so we're going to get dy over y equals 3x squared dx. And we can already see that we're almost ready to integrate it and solve for our function. If you remember from the calculus classes, that dy over y is really just the same thing as 1 over y dy, and just following along here, 3x squared dx. And so now you can see that we have ny is 1 over y, and then mx is 3x squared dx. And I think we'll just do it over here. And so what you can do is it'll just do integral of 1 over y, and then we have, 1 over y, I don't know why I erased that, 1 over y dy equals the integral of 3x squared dx. And so now this is just a natural log of absolute value of y plus some arbitrary constant, we'll call it c1, and this becomes x cubed plus some arbitrary constant c. Now when you do this type of integration problems, let's put c2. The only reason why I'm writing the constant on both sides is just so, just to illustrate the point that the constant of integration does exist for both of these integrals. But generally, because it's just a constant, it's arbitrary, it doesn't really matter what it is. Sometimes people just write the constant on one side. It doesn't really matter. You can kind of do whatever you want. This is really just to illustrate that the constant of integration comes out of both integrals, but it's not really important specifically what that is yet. Anyway, so here we have, so really we can even just get rid of this, and so we can just have ln y, absolute value of y, equals x cubed plus some constant c. Again, this constant doesn't really matter. Technically, you can just subtract this and bring it over here. It's an arbitrary constant. It's not really important. So anyways, to get rid of this natural log of y, we have to exponentiate both sides. So we basically have y equals e to the x cubed plus c. This right here is a solution to this differential equation. Now, in my introduction series, I showed you how to check to see if this is indeed a solution to the differential equation. And whenever you're doing a differential equation, it helps to check to see if it works. Because if you can plug this back into here and it works, then you know whatever you did was correct. So that's the nice thing about differential equations. You can always check yourself to see if you're right. So anyways, if we just, we can do that. So let's just say we have, so we had dy over dx, which is the same thing as writing y prime. So basically we have a function of y, so we want to take the derivative of this. And so what we can do is we can just do y prime equals 3x squared. Because remember, whenever you take the derivative of e to the something, you take the derivative of this, bring it out here, and then you leave the rest of it alone. It's just, chain rule stuff. And so my e did not look too good there. Okay, there we go. And then remember, whenever you take the derivative of a constant, the constant just drops out. So the c, not really important, is it goes away. And so here I say y prime, or dy dx, is equal to 3x squared e to the x cubed, and then that will just, and so this is equal to 3x squared times our function y, which is 3x cubed, and lo and behold, this is exactly the same thing. So this is a solution of the differential equation, and so now we're in business. So that's pretty much the basic way to solve these separable differential equations. Just really isolate your y's and x's. Don't forget that dy over y is the same as 1 over y, and then just follow the basic rules of integration and just check yourself, and you'll be in good shape. And now for initial value problems, which really, what initial value problems are is that you have, remember this is a general solution. I can, but what if we want to know what happens to the differential equation when x is equal to 1, x is equal to 2, we can plug that value in and see what's going on. So basically, so for y1, what did we say our y was e to the x cubed plus c, and so we can do y is equal to this, and so we can now plug in, let's see, so actually we should do it this way. We should say y equals, and this was equal to 4, but no, sorry, that was my bad. Just hold on, so this is equal to like 7 or whatever. So basically, the point is we're trying to find this constant, because this constant does change depending on what this initial value is. So this is why the constant is important, because we can observe certain properties of the differential equation based on the constant. And I talked about slope fields, or direction fields, in my introduction video, and later in a few videos I'll get more into that. But basically, this constant changes based on what goes on here. So we can do 4 is equal to e to the 1 cubed, which is 1, so e to the 1 plus c. So we can do 4 minus e is equal to c. That's what happens here. And then for this one, we can have 2, no, that's incorrect. 7 equals, it's right over here. So 7 equals e to the 2, e to the 8. Actually, I'm just going to go through that. It's getting a little messy over here, but so basically you have e to the 2 cubed plus c, and so 7 is equal to e to the 8, which is pretty large, plus c, and so c is equal to 7 minus e to the 8. Now you can see here that the constant behaves very differently as these values get larger and larger. So this is an interesting differential equation to take a look at. And basically this is kind of a good stopping point. So basically, just to recap, separable differential equations, they can be written as some function y dy, some function x dx, and you basically integrate both sides, and that is how you solve it. And keep in mind that whenever you have this form dy over dx, sometimes it helps to just multiply both sides of the equation by dx, and for several differential equations, this is often the technique that you use to solve them. It's kind of like one of the main tricks of solving them. And basically just follow the steps, check to see your solution is valid, and after your solution is valid, and then if there's an initial value problem, just go through it, find your constants, and you can kind of get an idea of how the differential equation behaves at different points. So anyways, that's a kind of a good stopping point, so I'll see you guys in the next video.